Hey guys, and welcome to another video in my A-level physics revision series. In this video we're going to be starting a new section. We're going to be starting the section on waves in the AS syllabus. And in this video we're just going to go over the basics of waves, and we're going to go over a bit about what some of the terms mean in the waves, a few of the basic wave equations, and looking at the sort of different types of waves. So like longitudinal waves, transverse waves, that sort of thing. So let's get started. First thing is, what is a wave? What actually is a wave? Well, basically a wave, and let's draw out a little wave right here. A wave is just any way of transferring energy from one point, say here, to another point. And there are various examples of wave that you're probably familiar with. You're probably familiar with sort of water waves along the ocean. So here are waves coming in, and they're traveling towards the beach right here. So here's the beach, and you've got the waves traveling in. And basically these waves are just carrying energy with them, and the energy is being transferred from sort of some distance out here, and it's being transferred over here. And it's doing it in a sort of a periodic manner, and anything which has like a periodic manner we call a wave. So it's a periodic way of transferring energy from one place to another place. There are of course different examples of wave. Of course light is a wave. Light is famously an electromagnetic wave that travels, that can travel through the vacuum. It travels indeed from the sun. So here's the sun. And the sun emits light, and this light travels 93 million miles, or 150 million kilometers, I must say, and hits the Earth, and that's why we're all alive, which is great and all. Other examples are things like maybe if you've got like a skipping rope or something, you can send a wave, like a pulse down the string or something like that, and you're carrying energy basically from one place to another. That is basically the point of waves. But you can also have waves that are slightly different. An example being sound waves. So what sound is essentially waves in the pressure between the source of wherever the sound's coming from and the receiver. So say you've got kind of like a noisy source right here. And you've got like a receiver, so here's maybe your ear. That's a very bad drawing of an ear, I know. But basically what sound waves are variations in the pressure or variations in the density of the air between the source and the receiver. So, but they're not actually waves as in this sense, because these are all what we call transverse waves. These guys all have their oscillations that are kind of up and down, whereas a sound wave has its oscillations kind of in and out, and I can draw what I mean by that. So you've got areas here where there's a very high density, but then you're going to have areas of low density, and these dots right here are just the air molecules. And then you've got a bit where there's high density, and so these are waves of density in the air, and that's what causes sound. So you're going to have, high density regions and low density regions, and high density regions and low density regions. And that's an example of a longitudinal wave. As you can see that the oscillations are kind of in and out rather than up and down. So transverse waves have a sort of up and down motion, whereas this wave right here, this type of wave, a longitudinal wave, has a sort of in and out, so sort of compression and what we call rarefaction, like sort of in and out as it propagates along. It's still propagating from here to here, you notice. This is still the direction of energy, but the oscillations are sort of in and out rather than up and down. Of course, another example is if you have, like, say, a slinky, then you can have sort of really tight bits, but then you can go and having really loose bits, and then really tight bits, and then really loose bits, and then really tight bits, and so on and so on. But these are what's happened when you're sending pulses down. So, you're going to have the direction of energy is still in this direction, but the oscillations are kind of in and out. Now there are various bits of a wave that you need to know about. So let's draw out a transverse wave to start off with. Let's draw out a transverse wave. So we're only going to draw one bit of a wave. This wave here is a typical transverse wave. And let's just give these a set of axes, because everything's better with axes, right? We sort of know what we're doing. So here are our axes. Let's call this axis the x-axis. And let's call this axis the y-axis. And we can see that this wave is traveling sort of in this direction here. It's traveling down the x-axis, but it's oscillating in the y-axis. So this is a transverse wave. The oscillation direction is perpendicular to the direction of energy transfer. Now there are various terms that you need to know about a wave. The first of which is displacement. Displacement is basically this quantity right here. Displacement, it's just the y. It's just this quantity right here. It's basically how far from the middle the oscillation is at any one point. So that's displacement, and it's typically measured in meters. Now this distance right here, the distance between the topmost point of the wave and the center, this is called the amplitude. And it's basically the distance between the center and the topmost point of the oscillations, and we typically give it the symbol A. It's the maximum displacement, and it's kind of constant for this wave here. You can see that this amplitude here is the same as this amplitude here. There's no difference between the amplitudes, and so it's constant for any wave. Whereas something like displacement, it could be anything. So here's maybe one displacement, y1. Here's another displacement, y2. All of these are displacements, but there's only one amplitude. And amplitude is, of course, again, measured in meters. Now, the next thing you need to know is the wavelength. And the wavelength, we typically give the symbol lambda. And again, it's measured in meters. And the wavelength is the distance between trough to trough, or peak to peak. In this case, I've drawn peak to peak. I don't know why I said trough to trough. That was very stupid of me. But it's this distance right here. And this is called the wavelength. It's the distance of one whole wave. So it's either crest to crest or trough to trough. This distance is also lambda right here. And again, it's constant for this wave that we're looking at here. The next thing is the period. And this isn't a distance, this is a time. Obviously a wave is a moving thing, and therefore there's time involved. And a period is basically the time taken for a whole vibration. So if you imagine this wave moving along the screen, it's the time taken to get from top to top. And we typically give it the period, the symbol t, and it's measured in seconds. Now, another very similar quantity is the frequency. Now, the period is the time taken for one oscillation, whereas the frequency is the inverse of that. The frequency is the number of vibrations in 1 second. So let me say that again. The period is the time taken for one oscillation, whereas the frequency is the number of oscillations in 1 second. And so it's easy to write that the frequency f is just 1 over the period. They're just the inverse of each other. And frequency is measured in hertz, and it's the number of vibrations per second passing a given point. And last but not least is the phase difference, and the phase difference is the amount by which one wave lags behind another wave. And the best way to illustrate this is if we have two waves. So let's say we've got a red wave and we have a blue wave right here. So these two waves, as you can see, they're not quite in phase with each other. You see, here we see the trough of this wave is not in line with the trough of that wave. So even though they have the same wavelength and possibly the same frequency, they aren't in phase with each other. There's a slight difference here. Whereas two waves that are in phase, so let's do maybe two waves that are in phase. Here's our yellow wave. And let's do a wave that's in phase. Here's a green wave. So we can see that these waves, even though I've drawn it very badly, you can see that this trough lines directly up with this trough here. This peak here lines with this trough here, this peak there rather. And so these two waves are in phase, whereas these two waves are out of phase. Now phase, you're wondering, how do you measure like that? How do you even like measure how different something is like that? Well, we actually measure it in radians, and radians are basically a measure of angle. Now, the reason why we measure them in radians is because there's a quite close analogy between sort of waves, oscillations, and a circle. And you can model a wave very similarly to how you can model a circle. One full rotation of a circle, so say we have a circle here, one full rotation of a circle can be thought of as sort of a whole period in time or in wavelength. And so the phase can actually be measured as an angle. So let's just write that down. Phase, and it's measured in radians. Now, to give you an example of how it works, these two waves right here, these two waves, the in-phase waves, have a phase offset of 0 degrees. If the phase offset is a multiple of 2 pi, and of course there are 2 pi radians in a circle, then the waves are said to be in phase. So these two waves have a phase offset of 0 or 2 pi or 4 pi. You could keep going if you want, but basically as long as they have a integer multiple of 2 pi, then they are in phase. Of course, 2 pi radians is exactly the same as 0 radians. See, with a circle, if you keep rotating around, then you're repeating yourself. 2 pi radians is exactly the same as 360 degrees, and so on and so forth. So if they're 360 degrees apart, they're also 0 degrees apart, because that's how degrees work, and so therefore they are in phase. Now if they're out of phase, then the angle is going to be somewhere between 0 and 360 degrees. Now the amount by which they're out of phase is exactly what the angle is. Now, I don't know quite how accurately I've drawn this, but two waves that are completely out of phase, if two waves are just completely out of phase, then they are 180 degrees out of phase, or pi radians, because there are pi radians in 180 degrees. And so if two waves are completely out of phase, then they are 180 degrees or pi radians. So maybe this wave is, if these two waves are completely out of phase, then they have a phase of pi or 3 pi or 5 pi, basically an odd number multiple. So pi is of course 180 or 540 or what would it be, 900 degrees. These are all degrees. Of course 900 degrees is just exactly the same as 180 degrees because it's modulated. So that's a little bit about what phase is. We might go into phase a little bit more in an upcoming video, but basically that's just what phase is. So what are the properties of waves? Well, there are 3 properties which are very important, and they're very defining of waves. So the first one is reflection. Now, you're probably fairly familiar with what reflection is. You have, say, a wave. Say you have a wave that's coming in, and say you have a surface here like a mirror or like a glazed surface. Then what's going to happen? Well, this wave is simply going to bounce off, but it's going to bounce off at an angle, and the angle of incidence here, let's say this angle here, is exactly the same as this angle here. The angle of incidence is equal to the angle of reflection. Now that's reflection. Refraction is slightly different. Refraction is the process by which a wave sort of changes direction when it enters a medium. So say you've got a wave that's traveling in air like this, but then it hits this sort of boundary here. Now this surface here is glass. This is glass. Now air bends slightly when it hits glass, and it does that according to what's called its refractive index, which again we'll come on to in a little bit later on. This also changes the angle at which the wave propagates. So basically going into a medium of higher refractive index changes the direction in which the wave goes. And this is called refraction. It's the changing direction when it enters a different medium. And the actual wave slows down and speeds up. So if it's coming from air, here and it enters glass, then the actual speed of the wave actually decreases because it can travel faster in air than it can in glass, because glass has a higher refractive index, but we will come on to that soon. So let's just go over a few of the basic equations regarding waves. Now, the one you're probably familiar with from GCSE states that the speed, which we give the letter v, is equal to the distance over time. Now, say we have a wave that's traveling. Here's our wave. It's traveling. Let's say it travels a distance lambda. So let's draw it after this whole wave has moved a distance lambda. So this distance here to here is lambda. Now, if we use our formula here that the velocity is distance over time, then we substitute in that the velocity is lambda. And what's the time period? Well, we said that the time taken for a wave to travel one full period is the period. It's this capital T right here. But we said that the period is the inverse of the frequency, because f equals 1 over t. Therefore, we can say that v equals f lambda. The wave speed is equal to the frequency multiplied by the wavelength. And this is such an important equation. It's basically how you convert between wavelength and frequency and speed, and it's a very fundamental equation. Now, the last thing I wanted to talk about in this video is polarization. And polarization is another property which is specific to waves. Only waves can do it. And so therefore, if you see polarization, then you know you're dealing with a wave. So let's say we have a wave that's traveling towards here. Now, the best way to envisage polarization is basically to imagine sort of like a fence, if you like, or a thing which kind of has lots of vertical bars in. Now, this wave is oscillating in this direction, up and down. And if we think about what the direction of this sort of gate is, it's also up and down. You know, the bars are vertical. They're vertical bars, and the wave is oscillating in a vertical direction. So what's going to happen when it hits the gate? Well, it's just going to carry on. The gate's not going to do anything at all to it. You know, it's going to continue to oscillate in an up and downy sort of manner. But what happens if we send in a wave that's not oscillating up and down, but is oscillating? It's kind of hard to draw it in 3D, but it's oscillating sort of back and forth almost. It's oscillating in this plane right here. If we maybe label a set of axes, then we can call this the z-axis, we can call this the y-axis, and we can call this the x-axis. And so we can see that this wave here is oscillating in the z-axis, and this wave here is oscillating in the y-axis. But what happens when this wave here hits the same polarizer, this same vertical polarizer? Well, if you think about it, nothing's going to get through, because this wave is oscillating in the y direction, but this polarizer is oriented in the z direction, and they're perpendicular, and so therefore no part of the wave is going to get through. So you'll just simply end up with a straight. There'll be no energy, there'll be no oscillation at all happening in this part of the graph. However, what if we take that same wave here, our same y oscillating wave, but this time, instead of passing it through a vertical polarizer, we pass it through a horizontal polarizer? Well, just like in the first example here, we can see that this is going to get through no problem at all, because the direction in which it's oscillating is in the y direction, But this time the polarizer is in the y direction, and so therefore it can get through perfectly fine, no problem at all. Now in these three examples, all of these cases are polarized light. This light here has been polarized in the z direction. This light here has been polarized in the y direction, as has this one here. Well, what is unpolarized light? Well, unpolarized light is basically just a mixture of all of these different types of light. So there might be some light oscillating in the z direction. There might be some light oscillating in the y direction. And also there could be anything in between. There's going to be light maybe oscillating at 45 degrees, pi over 4 radians. There's going to be light oscillating in this direction. And it's all mixed up in one. And so what's going to happen when it hits our polarizer? Well, if we have a vertical polarizer, then what did we see here? We saw that anything that was vertically polarized passed through, but anything which is not vertically polarized didn't pass through. So what's going to pass through here? Well, this does have vertically polarized light in. It does have some vertically polarized light in, but it's of course mixed up with other things. However, when it hits here, it's only the vertically polarized light that is going to make it through. It's that same vertically polarized light that was there before that can make it through. See, in this example here, there was no vertically polarized light, and so therefore nothing got through. But in this example here, there is some vertically polarized light, and so the vertically polarized light gets through. So a polarizer is just like a filter, if you like. If it's oscillating in the same direction, then it will get through fine. But if it's oscillating perpendicularly, it will not get through. What happens when we have a slightly odd scenario? Say we've got a wave which is oscillating at sort of 45 degrees. It's kind of oscillating vertically, but it's also not as perfectly as it was in this example here. And say, what if we have our vertical polarizer? Well, this right here, you can think of this wave as being a combination of z components of oscillation and y components of oscillation. So it's like a combination, and only the y component will be able to get through. And so therefore what you'll end up with is a wave that's kind of weakened a little bit. It's a kind of weaker wave. That was a really bad wave. Now you see, in this case up here, all of the light, because this was completely 100% perfect and polarized in the vertical, there was nothing to stop it from all going through, so it all went through. Whereas in this case here, only some of it, only say if it's oscillating at 45 degrees, then it's going to be half in the up and down direction and half in the back to forth direction. And so therefore only half of it will get through here. And so this amplitude here will be decreased by a factor of 2. And this effect is very useful for when we want to remove unwanted reflections and stuff. So you would often see things like Polaroid sunglasses, and they basically cut out the glare that you get from the sun on a hot summer's day, which is of course very useful. Another example of polarization in the real world is where you've got television and radio signals. If you have a look outside, then you'll often see these little things on the edge of houses like these. And what these are polarizers. These only allow waves of a certain direction to get through. And what you can do is you can move them. If you're not hearing it so great, you can adjust it so that it's parallel to the waves coming through rather, and therefore you'll get a much better signal. And these polarizers are there basically to cut off all the unwanted material carried in this wave, because of course this isn't going to be a simple wave like this. It's going to be a complete mess. It could be anything like that. It's going to be a complete mishmash of waves and all oscillating at different amplitudes, different frequencies. But these polarizers basically almost strip down the wave to the bits that you want. And the last thing to know is that materials can rotate the plane of polarization. So the plane in which a wave moves and vibrates is called the plane of polarization. So if we go back to our examples up here, then this this kind of plane of oscillation. This is the Z plane, and it's kind of like this. A plane is basically just an infinite sheet, if you like, an infinite 2D sheet, or an infinite sheet of paper, if you like. And this plane is oriented like this, whereas in this case here, the plane of polarization was oriented like that. And a material, so say like glass or something, a material can rotate the plane of polarization. So say you have a source of light coming here, and this source of light is going to emit a beam, and say you've got a polarizing filter oriented like this, and you've got a polarizing filter oriented like that. So what's going to happen? Well, this light here is going to be completely unpolarized. It's going to be a complete mess. It's going to be a mixture of horizontally and vertically vertical oscillations. This polarizer is only going to let through vertically polarized light. But when it gets to here, this polarizer is horizontally polarized. And so therefore, nothing is going to go through. The fact that these are both perpendicular means that nothing is going to go through. But what happens when we put a material between the two sources of light? Well, let's go and insert some kind of I don't know, maybe like a crystal or a piece of glass or something. Let's put it in between here. What's going to happen now? Well, we're going to have our unpolarized light as of before, and this is the material being tested. The vertical polarizer will vertically polarize the light. However, when it hits this, it's going to act a little bit like one of the filters. And so what it's going to do is it's going to change the direction. It's going to act like a bit like a polarizer itself. And if it changes the direction, then the light in this section is going to be different from the light in this section. And so when it passes through this, not all of the light will get completely blocked. There's going to still be some horizontal component getting through. So some of the light now gets through this filter right here. And what you can do is you can actually do something very clever. So say you've got this exact same setup, but what you now do is you can rotate this polarizer right here. You can rotate it. And so therefore you can rotate it to such an angle so that no light leaves the filter. And what this is going to do is this is going to measure how much this material right here will polarize. It's going to measure the polarizability, if that's a word. Who knows, it might be a word. And so you're going to have your unpolarized light coming in right here. It's going to vertically polarize this light, but this material, this crystal right here, is also going to polarize some of the light, and it's going to change the direction. And so it's going to change the direction to here, and if you rotate this until there's no light leaving, then you can find out how much this material changes the plane of polarization. So there we go. That is an introduction to waves. See you in the next video.